There's no beginning to the world. Not in the way you've been thinking about it. A beginning isn't an event. It's not something that happens once, and then you have a planet. A beginning is a physical problem, one that has to be solved over and over before anything qualifies as stable enough to matter. Most things that start don't persist. And if something doesn't persist, it doesn't become a world. It just becomes debris. When we talk about planetary formation, we're working at a scale where intuition stops being useful. A planetary disk around a young star isn't empty space with a few rocks floating around. It's a chaotic density field, gas, dust, ice, fragments of material colliding, sticking together, breaking apart. Temperature gradients that shift over hundreds of thousands of years. Gravitational turbulence from the star itself, from neighboring protoplanets, from anything massive enough to warp the local environment. The observable limits here aren't philosophical. They're physical. We can't see the early stages of planetary formation directly because light doesn't escape these regions well. And the timescales involved are measured in millions of years. What we know comes from models, from simulations, from studying other systems that might resemble what ours looked like. But the models all point to the same thing. Forming a planet isn't about assembling parts in the right order. It's about sustaining a process long enough for something to stop collapsing. Stop shattering, stop evaporating, long enough to hold together. Here's the problem that doesn't get stated clearly enough. Existence and persistence are not the same thing. A clump of matter can exist for a few thousand years. That doesn't make it a world. A protoplanetary body can accumulate mass, develop internal heat, even start differentiating into layers, and then get torn apart by a passing gravitational disturbance. It existed. It didn't persist. This channel uses persistence as the measuring standard, because it's the only criterion that separates transient structures from actual worlds. Without persistence, you don't have geology. You don't have atmospheres. You don't have oceans or magnetic fields or any of the systems that define what a planet is. You just have mass in motion, temporarily organized, waiting for the next disruption. If that distinction matters to you, if it changes the way you've been thinking about planetary origins, then hitting like helps signal that this approach is worth continuing. So what does the process actually look like when something tries to become a world? It starts with accretion. Small particles collide. Some stick. Electrostatic forces help at tiny scales. Gravity becomes relevant once you reach a certain mass threshold, maybe a kilometer across. Maybe less, depending on density and composition. But accretion isn't smooth. It's not additive in a clean sense. A growing planetesimal, let's say it's a few hundred kilometers wide now, pulls in more material. Impacts heat the surface. If the body's large enough, that heat doesn't radiate away quickly. The interior starts to melt. Differentiation begins, heavy elements sink, lighter materials rise. You get the early sketch of a core and a mantle. Then something larger hits it. Not a glancing blow. A direct collision. The energy released is enough to vaporize part of the surface, scatter fragments across thousands of kilometers. Maybe strip away whatever thin atmosphere had started to accumulate. What remains cools, resolidifies, starts pulling in material again, if it's still massive enough. If it's not, it becomes part of someone else's accretion process. This happens repeatedly. For millions of years. Picture it at smaller scale, a protoplanet about the size of Mars, surface temperature high enough to keep rock semi-molten in places, no stable crust yet. Constant bombardment from leftover planetesimals. That didn't get absorbed by the larger bodies. Each impact either adds mass or removes it, depending on angle, velocity, composition. There's no rhythm to it. No pattern. Just repeated attempts at cohesion that either hold or don't. Science models this through n-body simulations, tracking hundreds of thousands of interacting objects over time, calculating gravitational perturbations, collision outcomes, ejection velocities. The models suggest that most protoplanets in the early solar system didn't survive. They either collided with something bigger, got ejected into unstable orbits, or fragmented into asteroid-sized debris. The ones that lasted long enough to clear their orbital zones, to stop losing mass faster than they gained it, those became candidates for persistence. But candidacy isn't the same as success. If you're recognizing that this process isn't about assembly, it's about repeated survival, then subscribing means you're aligning with a method of thinking that doesn't stop at surface-level explanations. It continues past the comfortable parts. At some point, something changes. Not because of destiny. Because of probability and duration. A protoplanet reaches a critical mass threshold where its gravity becomes strong enough to hold onto lighter elements, hydrogen, helium, volatiles that would otherwise escape. Atmospheres start forming. Not from outgassing alone, but from captured material during accretion. The surface cools unevenly. And a fractured crust begins to stabilize in patches. Internal heat from radioactive decay and residual impact energy keeps the interior molten, which allows convection. Convection drives plate motion, or something like it, depending on the planet's composition and thermal regime. If the planet has enough mass and the right internal structure, it can generate a magnetic field, one that deflects charged particles from the star, preventing atmospheric erosion. These aren't solutions. They're reductions in instability. A planetary body doesn't solve the problem of persistence. It just reaches a configuration where the rate of disruption drops below the rate of stabilization. Impacts still happen. Volcanic resurfacing continues. Atmospheric loss still occurs, just more slowly. What started to work wasn't a mechanism. It was duration. The planet lasted long enough for internal processes to reach quasi-equilibrium. Long enough for a surface to cool into something semi-permanent. Long enough for volatiles to cycle between interior and exterior reservoirs without getting stripped away entirely. Earth, Venus, Mars, they all reached versions of this state. Not identical versions. Mars lost its magnetic field early, which meant its atmosphere thinned over billions of years. Venus kept its atmosphere, but developed a runaway greenhouse effect that locked the surface into a high-pressure, high-temperature equilibrium. Earth kept cycling. Oceans formed, evaporated, reformed, crust subducted, and renewed itself. The magnetic field persisted, fluctuating but never collapsing entirely. That's what starting to work looks like, not stability in an absolute sense, but instability that doesn't escalate past the point of system failure. Here's what we don't know. We don't know exactly how long it took for Earth's crust to stabilize enough to support oceans. Estimates range from a few 100 million years to over 1 billion. Depending on which isotopic evidence you prioritize and which thermal models you trust. We don't know whether Earth's magnetic field was continuous during the Hadean Eon, or if it collapsed and restarted multiple times. The rock record from that period is almost non-existent. Less than 1% of Earth's surface preserves any material older than 4 billion years. We don't know how many large impacts Earth sustained after the moon-forming event, or how those impacts affected the stability of whatever protocrust had started forming. The NICE model suggests a late heavy bombardment around 4.1 to 3.8 billion years ago. But the timing and intensity are still debated. And we don't know whether the conditions That allowed Earth to persist, specific orbital parameters, specific volatile inventory, specific thermal regime, were common in other planetary systems or rare enough that most protoplanets failed before reaching long-term stability. These aren't gaps that imagination can fill. They're limits in the observational record. Limits in our ability to reconstruct processes that happened over timescales longer than human civilization has existed. If you think these limits are worth challenging, or if you disagree with the framing, then ideas like this get sharper. When they're shared. When they're exposed to scrutiny outside the echo chamber of agreement. So here's where the definition of world stops being abstract and becomes a test. If a world is defined by persistence, then Earth had to pass that test. It had to last long enough, stay stable enough, hold together through enough disruptions to meet the criteria. But it didn't pass immediately. And there were periods, long ones, where it wasn't clear that it would pass at all. Early Earth wasn't stable. It was molten, fractured, bombarded, losing atmosphere, gaining atmosphere, cooling, reheating. For hundreds of millions of years, it didn't look like something that would last. It looked like something in the process of failing. And the question that opens up from this isn't whether Earth became a world. It's whether there was ever a point where it almost didn't. If that question creates enough tension that you need to respond, whether to argue, to clarify, to challenge the framing, then leaving a comment isn't optional. It's the natural consequence of unresolved ideas that refuse closure. The world didn't begin. It had to prove it could persist. And for a long time, that proof wasn't guaranteed.